Okay, so on Friday we were talking about finding the surface area of revolution and also the length of along a particular curve. So we looked at this function y equals 9 minus x squared, and we did the rotation around the x-axis. So first we're going to do it around the we're going to do now around the y-axis. So let's review what we did around the x-axis. So the formula, there's two ways of looking at it. You can do it with respect to x or with respect to y, irrespective of what variable you choose. So when we're rotating around the x-axis, the radius, the distance from the x-axis to the curve, is either equal to y or it's equal to 9 minus x squared, because the curve is not y equals 9 minus x squared. So they're equivalent to each other. It just depends whether you're integrating with respect to which variable. And the function, if you're going to do it in terms of x, then it has to be the derivative of that function with respect to x. If you're doing it with respect to y, you have to solve the relationship. Instead of y as a function of x, you have x as a function of y, and you take the derivative of that thing instead. And we came up with two equations, and they gave us the same answer either way. So you might choose the one that, if you were doing analytically, you might choose the one that was the easiest to solve analytically. I'm not sure if we knew how to do either one of them analytically. Just looking at this integral. Chapter 8, we would know how to do them, but we don't know how to do that yet. This one, definitely not. I'm not sure how to do that one. So what we're going to do now is just look at, instead of rotating around the x-axis, we're going to rotate around the y-axis. And you still have the same two equations. Surface area is equal to, what is the equation? 2 pi times the integral from a to b of, well, in this case, if you're going to put it in terms of x, you're going to have the radius, well, you're still going to have r of x, and you're still going to have the square root of 1 plus f prime of x quantity squared dx. It's just, in this case, instead of r of x being, it was either 9 minus x squared or y, it's the opposite, okay? So we're going to, in this case, let's write this down again. So this is around the y-axis. Just put this in your notes. So we're going to rotate around y-axis. So you can see over here, the distance from the y-axis to the curve is either going to be equal to x or it's going to be equal to the square root of 9 minus y. So in this case, r of x is equal to x. And then we have the square root of 1 plus, well, f of x is still 9 minus x squared, so f prime of x is still 2x. And that's squared dx. And we integrate from 0 to 3, because those are the x limits, from 0 to 3. The other version would be 2 pi times the integral from c to d of r of y times the square root of 1 plus g of y prime squared dy. So everything, the radius is in terms of y, and the derivative, the function, has to be a function of y. So g of y is this thing. We're just calling it g because we used f for the other one. So this would be equal to g of y, same as the previous problem. The previous solution, the only thing that changes, before when we rotated Excuse me. I've got this sore throat. I don't know what's had like 3 days now. And that's all I have. Okay, so r of y, when we did it before, was just y. In this case, r of y is that. So we're going to have the integral of 2 pi times the integral from 0 to 9 of the square root of 9 minus y. So that's r of y. And then you have 1 plus the derivative of this thing, which we found out was equal to what? It was equal to 1 over 2 square root of negative 1 over 2 square root of 9 minus y. So that's the derivative. So g of y equals the square root of 9 minus y. So if you use the chain rule, the derivative of this part is going to be 1/2, because you're to the 1/2 power, times 9 minus y to the minus 1/2 power. So you subtract 1 from the exponent, and then you multiply it by the derivative of the argument, which is just negative 1. So you can see that's, if you rewrite that back here, you'll get negative from here 1 over 2, there's 2, square root of 9 minus y. Okay, so that thing's squared, and this whole thing's square root dy. So both of these integrals should give us the same answer. And let's bring the ones we just did the other day next door and show you how they compare. So I'm gonna go and grab the ones we developed the other day. So we had this one. So let's take that. So that's kind of comparable with that. And then we had this one. Okay. Okay. So this was the surface area of rotation around the x-axis. So the radius was equal to y, or 9 minus x squared, which is the equation that defined that surface. Then we took the square root of 1 plus f prime of x squared. Over here, when we're rotating around the y-axis, the radius is x, but the inside, and I guess I should have put in, I have a negative there, and I don't have a negative here. Why did I? Oh, it should be negative. Yeah, it doesn't matter because it gets squared anyway. But this should be negative because it was negative 9 minus x squared. Derivative would be negative 2x. Okay, so this part changes, but this part doesn't change. Likewise, down here, when we rotate around the x-axis, the radius was y. Y equals 9 minus x squared, but the function, the function we use here is the solving for the boundary function 9 minus y equals 9 minus x squared, solving it for y, x equals a function of y, and then taking the derivative. So again, what we have different here is, instead of there we had y, here we have the square root of 9 minus y. Here we had x, and then we had 9 minus x squared. So it's just different ways of representing the radius. And also, when you're representing the radius as a function of y, you have to have this function inside here has to be the curve represented in terms of y instead of x. Okay, so now we're going to use our online integrator to see if we get the same result again. We showed that these gave us the same number. So we'll see if I did this right. If I did, then I should get the same answer. So here we go. We're doing this one. So it's going to be 2 pi. What am I doing here? All right, yeah, 2 pi from 0 to 3. So let me put that in there. 0 to 3, 2 times pi times x times square root of 1 plus negative 2x quantity squared. 1 plus negative 2x quantity squared. Okay, let's see if that looks right. 2 pi x square root of 1 plus, that looks good. Okay, so we'll say go. We'll get an answer, we'll write the answer down. So the answer is 111.3, 117.3. Okay, so we use the online integrator to get the answer, 117.3. And then we're going to try the second one. So we're going to integrate from 0 to 9 instead of 0 to 3. The radius is going to be equal to the square root of 9 minus x, 9 minus y. Is that right? Square root of 9 minus y. And the argument inside the square root is negative 1 over 2 square root of 9 minus y. Okay, so go here. So we have negative 1 divided by 2 times the square root of 9 minus y. So that looks right. Let's double check it. 2 pi, from 0 to 9, 2 pi square root of 9 minus y times the square root of 1 plus negative 1 over 2 square root of, okay, looks good. Push, oh, didn't, oh, dy, yeah, you're right. It won't like that. Yeah. How about dy? There we go. Well, actually, it assumed it was x, but let's see what happens. There you go, 117.3. So we got the same answer. Again, it's pretty impressive that they look so much different. They have different limits, and you get the exact same answer. So that should make you believe that math actually works. Like I said, we don't know how to solve that particular integral. I don't think we'll know how to solve that particular integral. Okay, we're going to do one more problem in this section, then we're going to move on to the next chapter. We may come back. We may come back and do some. I usually don't do the last couple of sections of chapter 7. So the good news is, I should tell you this 10 minutes later, but I don't put anything like this on the test. Okay, so it's sections 1 through 3. Okay, so if you felt like, oh my gosh, there goes one problem I'm never going to get, no, you're okay. So let's do one more problem. Unless you don't pay attention now. That's always the danger of saying you don't need it for the test. Is like, oh, okay, I can just. So this is another problem. This is finding the arc length of the curve 3/2 x to the 2/3 power. This is one of these lucky functions that you can actually solve without having to use the online integral calculator, I think. So because we're just doing the arc length instead of the area, it's the integral from a to b of 1 plus f prime of x squared, the whole thing square root dx. So the function is, the derivative of the function, you're going to take 3/2, the constant, times the numerator, which is 2/3, and you'll reduce the exponent by 1. So 2/3 minus 1 is -1/3, and the 2/3 and the 3/2 multiplied together give you 1. So you end up with x to the minus 1/3 power. And then you square that. So that's the integral. So then you square that, and I'm looking at that thinking I still don't know how to do that. Oh, maybe I don't know how to do that one. You square that because we're still actually there must be a solution to this. That's why in this particular section the integrals are really hard, or you revert to using the online integrator. So I'm sure I got this from the book. So there must be some way of doing it. So this is how would we? What could we do here? Yes.
I did it and I ended up using like 4 different substitutions.
Oh, really?
Trigonometric substitutions.
Trig substitutions? Really? Wow. Okay. That was probably not what they were expecting you to do. It may actually work. Did you get the right answer?
Yeah.
Okay.
I was just warning you.
Yeah, no, I think there's another way of doing it. And this is my thought here. If you think about it, if we could factor out so let's rewrite this as 1 plus 1 over x to the 2/3, like that. And if we multiplied and divided by, let's see if we multiplied by x to the 2/3. So what we're going to do is we're going to multiply by x to the 2/3 and divide by x to the 2/3 inside the square root. So what that'll do is, and I'll factor one of these out. It may not be exactly this, but I think this is the general gist of the idea. So when you factor, maybe it's to the 1/3. Let's try it to the 2/3. Okay, let's try the 2/3. So when you take this out, you take the square root of x to the 2/3, which is x to the 1/3. So the 1 in the numerator comes out of the square root because I'm multiplying this whole thing by x to the 2/3. So I take that out, and then what's left inside, I multiply. So this becomes x to the 2/3. Actually, it's in the denominator. And I don't think, this may not exactly. I think this is the general idea. I've just got to remember how to do this. Okay, so let's say. Now, actually, let's factor out the x to the 2/3 that's in the denominator. So you'll get 1 over x to the 1/3. So when you multiply this, you'll get x to the 2/3 plus 1. Is that right? So this comes out. Take the square root, becomes that. This times that becomes x to the 2/3. X to the 2/3 divided by x to the 2/3 becomes that. Now, if you let u equal x to the 2/3 plus 1, then du is going to be equal to 2/3 times x to the minus 1/3 dx, which is equal to 2 divided by 3 x to the 1/3. See? Yeah. You probably could do it the way you did it, but I think this is the easier way because we don't know trig substitution yet, but we'll get to that shortly. So as a consequence, 1 over x to the 1/3 dx. So what we'll get is dx divided by x to the 1/3 is equal to 3 du over 2. So what I did is I multiplied by 3/2 so that I got dx over x to the 1/3. So, and we'll go ahead and change, since it's a definite integral, we'll change the variables. So we'll say when x equals 8, u equals 8 to the 2/3 plus 1, which is 5. because the cube root of 8 is 2, and 2 squared is 4. 4 plus 1 is 5. And when x equals 1, u equals 1 to the 2/3 power, which is 1, plus 1, which is 2. So those are the changes of limits. So we can rewrite this integral as the integral from 2 to 5 of, I'm going to factor out the 3/2. 3/2 times the square root of u du. So you got 3/2. So you change this to a fractional exponent. Add 1 to the fractional exponent. So 1/2 plus 1 is 3/2 divided by 3/2. So those 2's cancel out, the 3's cancel out. And evaluate between 2 and 5. So you get 5 to the 3/2 minus 2 to the 3/2. And let's see if I got the right answer or not. So 5 to the 1.5 power minus 2 to the 1.5 power is 8.35, which is the right answer. How about that? So, so there's more. Yeah. When we get trig substitution, save that because that's pretty impressive. Yeah, and actually, since Evan brought it up, I've been saying we couldn't. I don't know how to do these problems. Well, we don't know how to do them yet, but this one that we did just a minute ago, this one is probably one that you would use trig substitution for. There are surprisingly a lot of integrals that you can do using trig substitution. Okay, so that's it for chapter 7. So the question is, what are we going to? I usually do a test on chapter 7. So probably at least one day this week we'll go back and try some more of these volumes of Revolution just one more time before we have the test. But I'm going to make the test next Tuesday, even though we're going to move ahead. Because Thursday's kind of early, and I like to have it on Tuesdays or Thursdays to give you guys a lot of time. So that's kind of the way that works out. So chapter 8 is basically going back and coming up with new ways of solving integrals. And the whole idea is to take an integral that's not in our table of integrals and somehow make some kind of substitutions so that it fits into the integrals that we know. So we're not going to develop any new integrals to stick in the table. We're just going to learn to manipulate stuff. The first section is kind of like a review of U substitution. Section 2, I think, is integration by parts. Section 3 is trig integration. Section 4 is trig substitution. Number 5 is partial fraction. Then we do something called L'Hopital's rule. So we'll talk about integrals with infinite limits, but not infinite answers. But the basic integral rules are the ones that are in your book. So these are the things we're going to cover in this section. So let me put this on one page. And as it says, you can solve the same integral using more than one technique. So we just saw that, right? as long as we believe Evan didn't make that up. But yeah, there's more than sometimes there's more than one way to technique to solve a problem. So what we're going to do is we're just going to kind of review U substitution again, because if you don't know U substitution, you're in big trouble. So these are the titles they use in the book: disguised forms, using trigonometric identities, adding, subtracting in the numerator. We've actually done some of that at the end of chapter 5, where we did some of the more complicated. They were kind of like rational functions, but having square roots in the denominator. Multiplying, dividing by the Pythagorean conjugate, and taking an improper fraction and dividing it out. So those are some of the things that we don't have to develop any new techniques or anything like that. We're just going to kind of review the things that we know. Okay. So the next view is just kind of a U substitution review. So what I'll do is, if you know how to do it, just go full blast. If you don't, this is a time to understand it. So remember, U substitution, you pick U as being part of the expression that's usually inside parentheses, inside of a square root, possibly the entire denominator, and then you take the derivative of that U to get du, and if the remainder, the part that doesn't include the term in the parentheses, matches up close enough except some constant difference, then a lot of times you're able to rewrite expressions. Most of the time it says polynomials, which are easy to do. That's one thing you guys do know how to do. Okay. So I'm probably just going to work these slow. And I'm not going to talk, so you can just work with me without me bothering you. And then if you have questions after, you can ask me to clear things up. And I'll just put the next page up, so if you get finished with that one, you can go to the next one. Okay, so I'll just leave that up for a minute, and you guys, if anybody has any questions, need me to explain it to you. So how many people watched the Tech UVA game on Saturday? Yeah, I forgot to watch it. I think it was actually Martha was interested. She's interested in the Olympics. She likes all the little personal stories. I don't think she cares too much about the sports, but she likes she likes the inspiring stories about different people. So we were watching that, and I think actually she might have gone to bed, and I saw something on Facebook, something about Hokies, and I'm going, oh no, I wonder when that was. And then I realized I missed it by about 2 hours. I'm not a very good alumni, am I? So did you understand all that? Yeah, okay. Oh, Spanish. You know how many years they've been doing that? Yeah, Heather did it when she was that was 2003, I think. Pinata. Oh, that's what it is, isn't it? A pinata. Cassie's it, I guess. She had all she.
Sisters, actually.
What's that?
These are my sisters.
Oh,
I
yeah.
already did it.
Oh, you've already
When I
done
was a
it.
freshman, so now
Oh,
I'm
is it a
just
freshman?
doing it again.
Oh, okay. Yeah, yeah. I remember Heather recruiting people for, I guess on the bus probably, going to school. Okay, we'll just do one more here. So let's see. Since u is the same between these two, I decided not to. It's 1 minus 2 square root of x. I just went straight down there. Notice, just for reference, so you don't notice how when I put the negative sign here, because of that negative sign, I put in the parentheses. I put in parentheses down here. Until you multiply it out or move it to the front, you always want to put it in parentheses so that you know that we're not subtracting du. Okay, so that's kind of, a lot of these initially look pretty complicated, but if you make the proper u substitution, they all come down to some kind of polynomial, whether it's a fractional exponent or a whole number or integer exponent. You just add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. Okay, I don't know if I got any more here or not, but I think I'm tired of doing this. So okay. So here are some of the trig identities that we'll use here. We'll also use them in some later sections in Chapter 8. So we have the Pythagorean identity, sine squared x plus cosine x squared x equals 1, and the two other ones that you can get from just for solving. If you solve for sine squared x or cosine squared x, then you've got the tangent squared of x plus 1 equals secant squared x, or you can solve for tangent squared instead of secant squared, and then you've got the corresponding ones for the cotangent and the cosecant. I only remember one of these. It's the first one, because I'm always sure I'm going to mess up the sign. So what I do is, to get from the one that's easy to remember because you use it the most, which is this one, if you divide by the cosine squared of x, every term is divided by the cosine squared of x. Like this. Sine over cosine is tangent, so you get tangent squared of x plus 1, because you're dividing by the same thing. 1 over the cosine is the secant, so that becomes secant squared x. And if you divide by the sine instead of the cosine, then you get those trig identities. So all you have to know is this, plus that the sine over the cosine is the tangent, and cosine over sine is cotangent. 1 over cosine is secant, and 1 over sine is cosecant. I don't know if there's any more down here. Oh, yeah, there's a whole bunch. Yeah, let's talk about that. So this is actually using the conjugate of a trig expression in terms of the denominator. So you might have, if I had the integral of 1 over the sine of theta plus 1, that's something that's not in our table. But if you multiply by the conjugate of the denominator, so we multiply both the numerator and the denominator by sine of theta minus 1 instead of sine of theta plus 1, what will happen is you end up with this arrangement where the inner and outer parts of FOIL cancel each other out and go to 0, And so you're left with sine theta times sine theta, which is sine squared theta. And then you have -1 from the last. And then you can use the first Pythagorean identity, the one involving sine and cosine, to replace sine squared theta minus 1 with negative cosine squared theta. And at first you may not think that's going to help you a whole lot, but if you write that as two separate fractions, so the advantage is you go from two terms in the denominator to a single term in the denominator, which then allows you to create two fractions. And so you'll have sine theta divided by negative cosine squared theta, which is this term, negative sine theta divided by cosine squared theta. And then you'll have negative divided by negative, so that cancels out. You get 1 over cosine squared theta. And ultimately, you end up with this expression. So the reason I broke this up, the cosine squared here into two parts, is because sine over cosine is tangent and 1 over cosine is secant. And so if I just, in terms of integral, if I had started with the original integral, 1 over sine theta plus 1 d theta, how do I integrate that? Well, you can see from my work here that I can replace the argument with negative tangent theta secant theta plus secant squared theta d theta. And the integral of secant tangent is secant. That's in the book. So that would become negative secant theta. And the integral of secant squared theta is tangent theta. And there's your answer. So again, it's all a matter of doing some whatever you need to do, whether it's trig identities or u substitutions, to take the original integral, which we don't have a formula for, and somehow get into something that we do have a formula for. And once you have the formula, then you just do it straight out of the book. So that's the conjugate, the Pythagorean conjugate example. The other identities besides the Pythagorean identity is just the definition of the trig functions in terms of the other functions. So tangent is sine over cosine, cosecant is 1 over sine, 1 over cosine is secant, cotangent could either be cosine over sine or 1 over tangent. Okay, so those are other identities. You don't have to memorize them because you get to use the cheat sheet. Or from now on, you actually, you basically get that handout that's in your tear out that's in your book. So you don't have to memorize any formulas or trig identities. The hard part is just using them. Okay, so here's another one. So what you're going to do is you're going to multiply by the Pythagorean, multiply by the conjugate of the trig term, and then use the other identities over here, including the one probably that involves secant squared minus 1. So you'll have to look back and see what that is. So I'll let you work this one out. So let's write that other. Let me just steal it from the other page if you didn't write it down. So it's one of these, probably this one. Probably that one right there. So I think I'll need to use that. And I just do the algebra first, or the trig first, whatever you want to call it. Yeah, Ian, in physics, he's taken second semester pre-calculus. They're doing trig identities right now. I was telling him the other day that We're getting to the part of calculus where you actually use trig identities. Oh, you're getting everybody to help you do. I see the two.
If you want, wants to roll. I'll bring you a bag if you want.
So give me something to do. Who was it last year? Somebody was really good at trig. Oh, it was Nate. Nate Brinkley. You remember Nate? he was he was like a savant on trigonometric identities. Just I sent him a Facebook message the other day. See how he's at Case Western in Cleveland. He's still there, so that's good. Doing well. Okay, I'm not finishing yet. So what I did was I multiplied and divided by secant of x plus 1. Not the secant of x plus 1, but the secant of x plus 1. And so when you use FOIL, the inner and outer terms cancel out. You end up with that, which fits that trig identity that I put up there nicely. So that becomes the tangent of x. So now what you need to do is rewrite the secant in terms of cosine and rewrite the tangent in terms of sine and cosine. And break that up into two fractions. One that'll be this divided by that, and one that'll be that divided by that. And 1 over the tangent is the cotangent. And I think, so the question is, is there a formula for the cotangent? I don't know if there is. Sometimes you have to go even further. I'm not sure. Cotangent. I'll come over and roll a couple more.
Cassie, what is she doing for her pinata? Shoot. Alright. It's like, she has a home plate. Okay. She's got a number on it. And then she's got a volleyball, a softball, and a basketball. She's incorporating all three of those when she plays. And it's a mess. It's a cool idea, though. Yeah, I think it's going to look really good, but there's a lot of colors. How big is it going to be? I think it's like this big. So it's really not bad.
Okay, so that's what I got. So for the first one, it's not as simple as the last one where we just ended up with something you could look up immediately. At this point, you'd have to use u substitution, where you'd let u equal the sine of x and du equal the cosine of x dx. So you'd end up with u squared du. It'd be 1 over u squared du. So then you'd integrate that. The integral, so let me just write that down. So for this one, when you actually integrate it, so the integral of 2/3 cosine x over sine squared x dx, you would say u equals the sine of x, so du equals the cosine of x dx. So this would become the integral of 1 over u squared du. So we could do that. And the cotangent squared, oh, I know what you have to do. So what you have to do with the cotangent squared, does anybody know what you might do with the cotangent? Because there is no integral that involves the cotangent. Yeah, that doesn't help, because you'd still have cosine squared over sine squared. You almost have to have like one thing here. If you have something squared, then there's just too many of them. Evan, what do you think? Okay. So what you would do, if you go back to, you could use this trig identity. So you have to use another trig identity. So 1 plus, the cotangent of x squared is cosecant of x squared minus 1. So, so let's come down here. So for this part, you would have 2/3 times the integral, and instead of the cotangent squared, you'd have the cosecant squared of x plus 1 dx. And this does, the integral of the cosecant squared is the cotangent, well, minus the cotangent. So we know that the integral of the this is the one that's in your book. The integral of cosecant squared dx is equal to negative the cotangent of x. And the integral of 1 is just x. So the next one would be the integral of 2/3. So this would be 2/3. And the integral of 2/3 dx would just be equal to 2/3 x. So that's how you would do it. So it's a trig identity within a trig identity. But ultimately, I was able to get it into things that I do know how to integrate. Here, using u substitution. So this one, when you integrate that, you'd end up with, so the integral of this, you'd have u to the minus 2 power, so the integral of that would be equal to u to the minus 1 power, u to the 1 power divided by negative 1, and then you plug u back in, so that u is the sine, so you get 2/3, negative 2/3 times 1 over the sine of x. Okay, because the integral of this would be u to the minus 1 over negative 1. So the negative from there is there, and u is sine of x. So sine of x to the minus 1 is 1 over the sine of x. So that'd be the first part. Then this part, the integral of the cosecant is going to be equal to negative the cotangent of x. And then the final one is the integral of 2/3 dx. This would be 2/3 x plus c. And if I'd done that about a few years ago, I probably wouldn't have remembered what to do. But so, don't be. I'm not going to put something that you just have to be thinking the right way the right day, or you have 7 years doing these kinds of problems. So, but it does demonstrate that you can start with something that you can't integrate, and you just keep going. That's the thing about trig identities. A lot of times you don't get them the first time. You just have to keep